Have you ever paused to truly consider the invisible, intricate web of safety management that goes into every single electrical and electronic system in your car? It's not just about the airbags deploying in a crash, or the braking system engaging flawlessly.
Right. There's so much more beneath the surface.
Exactly. It's about the rigorous processes, the deeply embedded culture, really, and the unwavering commitment behind their flawless operation. This isn't merely a technical standard, you see. It's a profound blueprint for confidence, for that feeling of absolute security every time you get behind the wheel.
Absolutely. And when you think about the sheer, dizzying complexity of modern vehicles, from their advanced driver assistance systems that help you stay in your lane or brake automatically, to the intricate engine controls and, the growing autonomy that allows cars to almost drive themselves.
Incredible.
The layers of safety required are just astounding. It's not just a feat of engineering. It is, perhaps even more critically, a triumph of systematic management.
And today, we're taking a deep dive into a very specific yet incredibly crucial piece of that colossal safety puzzle, ISO 26262-Part, formerly titled Road Vehicles Functional Safety Part 2, Management of Functional Safety.
Okay.
Now, this is a cornerstone of the larger ISO 26262 series, which, for anyone listening who might be less familiar, is the international standard for functional safety in road vehicles.
The big one for automotive safety.
Yeah. Our mission today is to truly unpack what this particular part of the standard means for everything from your car's automatic emergency braking system to its core engine control unit, and even the intricate sensors feeding it information.
Our insights for this deep dive are drawn directly from the 2018 edition of this international standard itself. And let me tell you, it's a dense document. Oh, yeah.
Yeah.
Packed with technical requirements and detailed clauses.
Yeah.
But our goal isn't to read it to you like a textbook, right?
Definitely not.
Our mission today is to distill the most important nuggets of knowledge, giving you a shortcut to being truly well-informed about how vehicle safety isn't left to chance, but is instead systematically managed. From the very top levels of an organization right down to the individual lines of code and the tiny components.
Our ultimate goal here is to go beyond the intimidating technical jargon and understand the organizational, the process-oriented, and, I'd argue, most importantly, the human elements that are absolutely critical to building safer cars.
The human factor. Always key.
Think of this as getting a behind-the-scenes look at how vehicle manufacturers ensure that electrical and electronic systems behave exactly as they're supposed to, fundamentally reducing risks from both systematic failures. Those are issues inherent in the design or the process itself.
Right. Predictable flaws, in a sense.
And random hardware failures, the kind that can occur unexpectedly due to wear and tear or, manufacturing defects.
And predictable ones.
We're going to cover everything from how companies foster a safety-first culture at their very core to how they meticulously handle problems when they inevitably arise. Because in complex systems, issues always crop up.
Always. It's about how you manage them.
So with that in mind, what exactly does this standard set out to do, and where does it begin? Let's unpack this.
All right, let's start with that foundational question. What exactly is ISO 26262? At its core, Part 2 is entirely about the management of functional safety.
Okay, management.
Yeah, it's not, as you might first assume, about the intricate technical design of a specific circuit or particular line of code or, the physics of how a component fails.
Not the nitty-gritty engineering details, then.
Not directly in Part 2, no. Instead, it lays down the comprehensive framework, the overarching rules, and the precise responsibilities for ensuring safety throughout a vehicle's entire lifecycle.
So it's less about how to build a safe component and more about how to manage the entire process of building and maintaining safety from conception to retirement? Is that right?
Precisely. It provides a structured, almost architectural approach to safety that is designed to be integrated seamlessly into a company's existing development framework.
Integration. That's important.
Very. This part of the standard really zeroes in on establishing and demonstrating an organization's capability in functional safety. And it applies specifically to safety-related electrical and/or electronic, or EE, systems.
EE systems, got it.
That are going into series production road vehicles. This means it's for the cars, trucks, and buses that you and I see on the road every single day. Not one-off prototypes or experimental vehicles.
That distinction that it's about the management and applies to series production vehicles is really important. And what does it not cover directly? Because sometimes knowing what's outside the scope helps clarify what is inside.
Good point, yeah. While it's fundamentally about safety, It doesn't directly cover hazards like electric shock, fire, or radiation in a general sense.
Okay.
However, and this is crucial for its application, it does step in if those hazards are directly caused by a malfunctioning EE system.
Ah, okay. So the EE system has to be the trigger.
Exactly. So if your car's EE system malfunctions in a way that, say, leads to an electrical fire, then that specific scenario is within scope. But if the fire is due to, for instance, a fuel leak unrelated to the EE system, then that's generally outside this standard's direct purview. It's very focused on the EE system's functional behavior and its potential for unintended or hazardous operation.
Okay, so it's about the behavior of the electronic brain of the car, essentially, and its safety implications. And what about the types of vehicles? Does this apply to absolutely every single vehicle on the road?
Not quite every single one. The standard specifies some particular exclusions. For instance, mopeds are out,
Mopeds, okay.
as are highly unique E-systems designed specifically for drivers with disabilities. The standard also provides some important context regarding its application date. Crucially, systems that were already released for production or under significant development before its 2018 publication are generally exempt for this edition's scope.
Ah, grandfathering in older systems.
Sort of, yes. However, and this really highlights its adaptability and forward-thinking nature, it does provide comprehensive guidance for alterations to existing systems and, significantly, for the integration of legacy systems into newer designs.
Oh, that's key.
Yeah, it ensures that even older designs, if modified or incorporated into a new platform, still get the benefit of the latest safety treatment.
That flexibility makes a lot of sense. You wouldn't want to force a complete recertification of an entire vehicle line every time the standard gets an update, especially with how long vehicle platforms typically last.
Right. It would be impractical.
But you definitely want to ensure that any new changes or integrations meet the absolute latest and most rigorous safety requirements. I also noticed that the standard specifically mentions adaptations for motorcycles, which is ISO26262-Part.
Oh.
And then for trucks, buses, trailers, and semi-trailers, often referred to as T&B. That indicates its broad and growing reach across the entire road vehicle industry beyond just passenger cars.
Absolutely. The standard is designed to be comprehensive and adaptable across the diverse landscape of road vehicles. And speaking of its evolution, the 2018 edition got some really significant technical revisions compared to the first edition from 2011.
Okay, so it evolved.
Oh, yes. These weren't just minor tweaks. They reflect a continuous learning and improvement cycle within the standard itself. A responsiveness to new technologies, new industry practices, and importantly, new challenges that have emerged in the intervening years.
Tell us about some of those key changes that jumped out at you. What were the big ones?
Well, as you mentioned, the inclusion of specific requirements for trucks, buses, trailers, and semi-trailers. The T&B stuff was a huge step, broadened its industrial application significantly.
Right.
The vocabulary was expanded for greater clarity and consistency across all parts of the standard. There's also much more detail now on objectives and objective-oriented confirmation measures, which we'll delve into later. These are the independent checks and balances that are so vital.
Okay, the checks and balances.
A crucial new addition was the detailed introduction of the management of safety anomalies. This means having clear, documented processes for handling deviations, unexpected behaviors, or discovered issues that could impact safety throughout the lifecycle.
Handling problems systematically.
Exactly. But perhaps the most significant and certainly the most forward-looking change was the direct references to cybersecurity.
Ah, there it is, cybersecurity.
This is a colossal one.
Yeah.
Explicitly acknowledging the growing awareness of new threats originating from malicious intent that can directly impact functional safety.
That's truly fascinating. Cybersecurity is such a huge topic right now, and to see it directly integrated into a functional safety standard really shows how interconnected these areas are becoming and how our definition of safety is constantly evolving.
Indeed. Beyond that, there were updated target values for hardware architecture metrics, which are crucial for quantifying the safety of hardware. There was also enhanced guidance on model-based development.
Which is huge in software now.
Increasingly prevalent, yes, along with more sophisticated software safety analysis techniques. The standard also improved its evaluation methods for hardware elements and provided additional refined guidance on dependent failure analysis that's about identifying if a single fault could propagate and cause multiple failures.
Cascade failure.
Precisely. Plus, the specific requirements for motorcycles, as you noted, and a general restructuring of all parts for improved clarity and navigability, All these changes collectively indicate a maturity and a responsive nature of the standard to the rapidly evolving automotive landscape.
Okay, so ISO 26262 is this comprehensive management blueprint. But where did this blueprint actually come from? It didn't just appear out of thin air, right? What's its intellectual bedrock?
You're absolutely right, it didn't. ISO 26262 is actually an adaptation of a broader, more general and foundational standard, the IEC 61508 series.
IEC 61508.
That series covers functional safety for electrical, electronic, and programmable electronic safety-related systems across a vast array of industries. Think industrial automation, medical devices.
Right, other safety critical areas.
Exactly. ISO 26262 took those core, robust principles and meticulously tailored them specifically for the unique needs and complexities of the automotive sector. From the fast-paced development cycles to the highly specific operational environments and failure modes of road vehicles, it's taking lessons learned from other high-risk industries and applying them to the car.
And a core conceptual model that underpins the entire standard, something that many engineers will be familiar with, is the V model. For those of us who aren't engineers staring at flowcharts all day, can you help us visualize this?
Certainly. Yeah, imagine the letter V itself.
Okay.
On the left side, as you conceptually go down, you have the progressive refinement of the system. This side represents the creation phase. You start with very high-level safety goals, then you break them down into increasingly detailed functional requirements, then into technical requirements, then you design the hardware and software components, and finally you implement them. So it's about specification and design, getting more detailed as you go down.
And then the V turns the corner and starts heading up.
Exactly. The right side of the V represents the integration, verification, and validation phases. This is where you test and prove that what you've created actually works safely and as intended, and that it meets those initial high-level requirements.
The proving ground.
Essentially, yes. You integrate software modules, that hardware and software, you verify individual components and subsystems, and finally, you validate the overall functional safety at the vehicle level. Part 2, the management part, orchestrates the entire safety lifecycle across all these phases. From the initial concept, through product development at the system, hardware and software levels, all the way to production, operations, service, and even decommissioning of the vehicle.
Wow.
It's the overarching guide for that entire V-model journey, ensuring safety isn't just a design afterthought, but is rigorously tested and confirmed at every step.
That makes it much clearer. It's not just a set of rules, but a systematic process model that dictates how you approach safety from start to finish. So how do organizations actually comply with this standard, and how are these requirements interpreted, especially with those different levels of safety integrity?
That's a critical point, and it speaks to the rigor. When an organization claims compliance with ISO 26262, every requirement must be met.
Must be met. No exceptions.
Well, very little wiggle room. There are a couple of very specific exceptions. A requirement might not apply if a project-specific tailoring has been performed and robustly justified.
Okay, tailoring with justification.
Or if a documented rationale for non-compliance is provided and meticulously evaluated. This highlights a fascinating balance. Rigor is paramount, but there's also a built-in, carefully controlled flexibility to adapt to truly unique project circumstances, provided it's transparent, thoroughly documented, and convincingly justified.
So it's not a one-size-fits-all, but you better have a profoundly good documented reason if you're deviating.
Precisely. And this leads us directly to the concept of automotive safety integrity levels, or ASILs.
ASILs, right? I heard that term.
This is central to ISO 26262 and one of its most defining features. ASILs range from A to D, with ASIL D representing the highest level of automotive safety integrity and thus demanding the most stringent requirements.
D is the highest risk, highest rigor.
Correct. These integrity levels are critical because they directly dictate which specific requirements of ISO 26262 are applicable to a given system or component, helping to ensure that any unreasonable residual risk is avoided. Think of it as a spectrum of risk, and the higher the ASIL, the more robust, meticulous, and independent your safety measures and processes need to be.
So if a system is deemed ASIL D, perhaps a core component of a highly autonomous driving system, it faces the most intense scrutiny and has to adhere to the most rigorous practices outlined in the standard. But how does that play out in real systems?
Exactly. Requirements generally apply across all ASILs A, B, C, and D, unless explicitly specified otherwise in the standards tables. Now, a key practical consideration, especially for an informed audience like yours, is ASIL decomposition.
Decomposition, breaking it down.
Yes. This is where a high ASIL requirement, say an ASIL-D, is broken down into lower ASIL components during the architectural design phase. For example, an ASIL-D system might be architected such that parts of it are ASIL-B and ASIL-C, maybe with additional mechanisms to ensure the overall ASIL-D safety goal is still met.
Ah, interesting. So you can manage complexity that way.
You can, but it's crucial for breaking down complex systems into manageable parts. However, this isn't without its challenges. The key is ensuring that when you break down a highly critical ASIL-D requirement, you don't inadvertently create gaps in safety coverage, or that the interfaces between those decomposed components aren't where new, unforeseen risks emerge.
Right. The interfaces are always tricky.
Always. The standard implicitly pushes for meticulous coordination and analysis here to ensure the sum of the parts still achieves the original, higher safety integrity. And the standard also uses specific notation in its tables for recommendations. You'll see all for highly recommended methods, plus all for recommended, and O for no recommendation for or against.
O, got it.
It even clarifies how to apply consecutive versus alternative entries for methods, demonstrating the incredibly detailed guidance provided to ensure consistent and robust application across the industry.
So we've set the stage with what ISO 26262-Sys2 is and how it functions as a management framework. Now let's truly get into the nuts and bolts, starting with overall safety management, which is covered in Clause 5 of the standard.
Clause 5, right.
This section really focuses on the prerequisites, the foundational, overarching organizational capabilities that must be firmly in place before any specific project-level safety activities even begin. It's about setting the organizational stage for safety success even before a single line of code is written or a component is designed.
That's right. The first and perhaps most intangible, yet utterly vital element here is safety culture.
Safety culture. Okay. That sounds important, but maybe a bit fuzzy.
It can sound fuzzy, but the standard is explicit and uncompromising on this point. Organizations must create, foster, and sustain a safety culture that genuinely supports and encourages the effective achievement of functional safety. This isn't just about putting up motivational posters or having a mission statement on the wall.
Right, not just lip service.
No, it's about promoting deeply effective and transparent communication across all related disciplines, from engineering to manufacturing, from legal to sales.
And the standard goes surprisingly deep into what constitutes a good versus a poor safety culture, even providing concrete examples in Annex B. I think it really brings the concept to life for listeners, so let's unpack some of those, because it gets to the heart of why this isn't just a feel-good statement, but a non-negotiable insight.
Absolutely. A good safety culture, for example, is one where accountability for safety decisions is clearly traceable. You know who made what decision and why.
Traceability.
Okay, safety is truly the highest priority, always, not just when it's convenient or cheap. Reward systems are designed to motivate functional safety achievement, not just speed or cost, potentially penalizing those who cut corners.
Incentives aligned with safety.
Exactly. Processes provide adequate checks and balances, perhaps even mandating independence in integral processes like verification and validation. Intellectual diversity is actively sought and valued, meaning different viewpoints, even dissenting ones, are welcomed and explored.
Encouraging constructive disagreement.
Yes. Self-disclosure and the proactive discovery of issues are not just tolerated, but actively encouraged, fostering an environment where problems are brought to light immediately, not hidden. Continuous improvement is integral to every process, and defined, traceable, and controlled processes are diligently followed at all levels of the organization.
That sounds like an ideal organization. What about the flip side? What characterizes a poor safety culture according to the standard, and why is that so dangerous?
Well, in a poor safety culture, accountability often isn't traceable. Issues seem to disappear into a bureaucratic black hole.
Sounds familiar in some places.
Unfortunately, yes. Cost and schedule consistently take precedence over safety, creating immense pressure. Reward systems might inadvertently penalize those who prioritize safety if it impacts deadlines or budget. Personnel assessing safety can be unduly influenced, perhaps by management pressures or internal politics, compromising their objectivity.
Undue influence. Big problem.
Huge. There's often a passive attitude towards safety, with heavy reliance on end-of-development testing to catch issues rather than proactively preventing them earlier in the design phase. Resources aren't adequately planned or allocated for safety activities. There can be pervasive groupthink, where dissenting voices are ostracized or labeled as not a team player,
Ooh.
leading to critical safety warnings being ignored. And crucially, There's no systematized continuous improvement process. Lessons from failures or near misses are quickly forgotten.
So it's not just about having the right procedures on paper, but whether the actual environment and mindset of the people allow those procedures to flourish. Historically, major safety failures, whether in industrial accidents or large-scale automotive recalls, often trace back not just to a technical flaw, but to a deeply embedded culture where issues were hidden, ignored, or where deadlines constantly trumped safety.
That's exactly right.
So this cultural foundation truly underpins all technical and process-driven safety efforts, making it absolutely critical.
That's precisely it. Beyond culture, the standard requires organizations to institute and maintain specific organizational rules and processes to comply with ISO 26262. This isn't about project-specific plans yet, but about creating generic plans, like a generic safety plan, or detailed process descriptions that apply universally across multiple projects within the organization. It's about having a standard operating procedure for safety.
Setting the baseline for everyone.
Exactly.
And then there's the inevitable problems. How does the standard address the management of safety anomalies, which sounds like a very polite term for things going wrong?
It is indeed a polite term, but it's a crucial area. Organizations must have robust processes in place to ensure that any identified safety anomalies, any deviation or unexpected behavior that could potentially impact safety, are explicitly communicated, thoroughly analyzed, meticulously evaluated, decisively resolved, and finally managed to closure in a timely and effective manner.
Managed to closure, meaning?
Meaning the standard is very clear that a safety anomaly is only considered closed if one of two very specific things happens. Either an adequate safety measure is implemented to resolve it, and its effectiveness is rigorously verified based on a clear documented rationale.
So you fixed it and proved it's fixed.
Right. Or the anomaly is evaluated as not constituting an unreasonable risk, and it's closed based on an equally strong documented rationale. This prevents problems from simply disappearing.
So you can't just sweep a problem under the rug or hope it goes away. It needs to be definitively addressed and either truly fixed or demonstrably proven not to be a significant risk.
Exactly. The documentation and escalation requirements here are designed to prevent issues from dying on the vine, ensuring visibility even up to the highest levels if they're not fully resolved.
Escalation. So it goes up the chain if needed.
Yes. If a safety anomaly isn't managed to closure within the agreed-upon time frame, it must be escalated to persons responsible for functional safety, such as a project manager, or even the person responsible for the functional safety assessment. This ensures that critical issues don't fall through the cracks, ever.
Beyond processes, the standard also heavily emphasizes competence management. What does that entail? Is it just about hiring good engineers?
No, it's far more comprehensive than just hiring good people. This is about ensuring that all persons involved in the safety lifecycle, and that means a lot of people, not just safety engineers.
Right, manufacturing, service.
Yeah, exactly. Have sufficient skills, demonstrable competence, and appropriate qualification for their specific responsibilities. Examples of critical knowledge areas include usual safety practices, general concepts, and designs. A deep working understanding of the ISO 26262 series itself, the organization's specific safety rules, established rules for interacting disciplines, and the organization's precise functional safety processes.
Wow, that's a broad range of knowledge.
It is. Practically, evaluating skills can involve looking at a candidate's or employee's experience in domain knowledge, their environmental expertise, management capabilities, and even their experience in production, operations, service, and decommissioning phases. It's about a holistic view of the human capital driving safety.
So it's not just about having a safety manager. It's about ensuring everyone touching the project understands their role in safety and has the capability to fulfill it. And this leads to another important integration point, the quality management system, or QMS. How does that fit in?
Yes. The standard explicitly requires that a robust quality management system be in place that demonstrably supports functional safety and complies with a recognized international standard, such as IATF 16949 in conjunction with ISO 9001.
IATF 16949, the automotive quality standard.
That's the one. This demonstrates the standard's understanding that safety isn't a siloed activity that you bolt on at the end. It's fundamentally integrated into broader quality frameworks. Good quality management practices, with their emphasis on process control, documentation, and continuous improvement, are a powerful and essential enabler for good functional safety. They work hand in hand.
Integrated safety and quality. Makes sense.
Definitely.
And finally, under overall safety management, we have project-independent tailoring. This sounds like it offers some flexibility, which seems rare in a standard this rigorous.
It does, but it's a very controlled flexibility. It means that organizations can tailor the safety lifecycle for application across multiple items or elements, meaning tailoring that applies generally across the organization, not just to a single specific project.
Okay, tailoring, that's not just project by project.
Right. This project-independent tailoring is limited to very specific modifications, such as combining or splitting phases in the safety lifecycle, performing activities in different or added phases, iterating phases, or performing activities concurrently. They can even omit non-applicable phases. But crucially, this must be done with a clear, robust, and documented rationale that demonstrates how functional safety is still maintained.
Rationale is key again.
Always. This flexibility acknowledges that different organizational structures, product types, and development methodologies might require slight adjustments to the standard's general recommendations while still rigorously maintaining the core safety objectives. It's about making the standard practical without compromising its intent.
So all these foundational elements, the safety culture, the organizational processes, anomaly management, competence, quality, and general tailoring, must be in place before a project even truly gets going. And what are the tangible outputs, the work products from this overall safety management? What's the proof?
The standard specifies these as several key documents and pieces of evidence. The organization-specific rules and processes themselves, clear evidence of competence management across relevant personnel, demonstrable evidence of a functioning quality management system, and of course, any identified safety anomaly reports, complete with their closure rationales. These are, in essence, the verifiable proof points that an organization has built and maintained a robust foundation for functional safety.
All right, so with the organizational foundation firmly in place, that deep-seated safety culture, the robust processes, the trained personnel, let's move into Clause 6, project-dependent safety management.
Clause 6. Okay.
This is where the rubber truly hits the road, detailing the hands-on, day-to-day management activities that occur specifically during the concept and product development phases for a particular vehicle system, for that specific item, as the standard calls it.
Indeed. The objectives for this clause are very precise, almost like marching orders for a safety project. They include meticulously defining roles and responsibilities for everyone involved.
Who does what?
Exactly. Performing rigorous impact analyses for any modifications or reuse of existing components, meticulously tailoring specific safety activities with solid justifications, and planning and coordinating everything down to the finest detail. It's also about ensuring the correct progression of the safety lifecycle from one stage to the next, building a comprehensive safety case to formally argue for the achieved safety.
The safety case.
Judging that achieved safety through independent means and ultimately making the absolutely critical decision to release the item for production.
And speaking of roles, who are the key players on a safety project and what are their responsibilities? Because in an orchestra, everyone has a part, and here everyone has a role in safety.
The standard outlines two primary, absolutely central roles. First, the project manager. Yep. This person is appointed right at the project's initiation and holds the ultimate responsibility and authority to ensure that all safety activities are performed diligently and that compliance with ISO26262 is achieved. They also have the responsibility to verify that sufficient resources, both human and financial, are provided to achieve those safety objectives.
So for safety, the buck stops squarely with the project manager. They're the captain of the safety ship.
In essence, yes, they bear the ultimate accountability. Then there's a safety manager.
Safety manager. Okay, different role.
Often, yes. This role is appointed by the project manager. And interestingly, in some smaller organizations or projects, it can even be the same person, though often it's a dedicated specialist.
Ah, okay.
The safety manager is specifically responsible for the detailed planning and meticulous coordination of safety activities, for maintaining the central safety plan, and for diligently monitoring its progress throughout the project. They can also delegate specific safety tasks, but the overall responsibility for the plan remains with them.
So the PM is overall responsible. The safety manager manages the day-to-day safety plan.
That's a good way to put it. And it's crucial to note that in cases of distributed development, where work is shared between, say, a vehicle manufacturer and a supplier.
Which happens all the time.
All the time.
Yeah.
Both parties appoint their own project and safety managers to ensure clear lines of responsibility and communication. These are formalized through what are called Development Interface Agreements, or DIAs.
DIAs, okay, defining that relationship.
Precisely. Clear accountability and defined interfaces are vital in such complex undertakings.
Now, you mentioned impact analysis. This sounds like it's about understanding how changes, even seemingly small ones, might ripple through a system and affect safety. How critical is this, and what does it actually involve?
Impact analysis is incredibly critically important, and it's a process that happens at two distinct levels. First, the item-level impact analysis, which is covered in Clause 6.4.3.
Item up.
Its fundamental purpose is to determine whether the item you're working on is a brand new development, a modification of an existing item, or an existing item with a modified environment. This initial determination sets the entire stage for how you tailor the rest of the safety lifecycle for that specific project. If it's a modification, you need to identify very precisely what has changed.
So, what kinds of modifications are they looking for? Give us some quick examples.
It's quite comprehensive. It includes design modifications, such as altering the software's logic for an autonomous parking feature, or changing the calibration data for an engine control system.
Calibration changes count.
Oh, yes.
They?
Then there are implementation modifications, like a small code correction in the braking system. Even if the underlying design specification isn't intended to change these, can still have subtle but critical safety implications.
Even bug fixes.
Even bug fixes.
Yep.
And finally, environmental modifications, which can be anything from installing the item in a new vehicle variant that has different weight distribution or aerodynamic properties.
The context changes.
Exactly. Changes to its operational situations, like using it in off-road conditions versus urban driving, or even just a different physical location within the vehicle, or broader environmental factors like extreme temperature ranges or electromagnetic interference levels.
So if you take an existing engine control unit, proven in one vehicle, and put it into a completely new vehicle model or modify its operating conditions, that's an environmental modification that absolutely needs an impact analysis.
Absolutely. Once these modifications are identified, you must then rigorously evaluate their implications on functional safety and identify the specific targeted safety activities that need to be performed as a result. This ensures that changes, even seemingly minor ones, don't inadvertently introduce new hazards or compromise existing safety measures. It's a proactive risk assessment.
And what's the second level of impact analysis?
That's the element-level impact analysis, specifically for reuse, covered in 6.4.4.
Element level for reuse.
Yes. This comes into play when an existing element, perhaps a common software module, a generic control algorithm, or a specific hardware component like a microcontroller, is being reused in a new, different context. The process here is to identify any modifications to its new operational context, then meticulously evaluate whether the element, with or without any necessary changes, still fully complies with the safety requirements in its new environment. You identify any necessary additional safety activities, and you assess if the existing safety documentation for that element is still sufficient for its new application.
That sounds like it allows for a lot of efficiency. You don't have to reinvent the wheel every time you want to use a component that's already proven.
Exactly. This flexibility is key for efficient development in the automotive industry, where component reuse, or leveraging pre-developed intellectual property, is incredibly common. Elements can be reused based on a formal hardware element evaluation, a software component qualification, a proven-in-use argument.
Proven in use, meaning it's been out there working safely for a while.
Essentially, yes, demonstrating safety through extensive field experience in similar applications, or as a safety element out of context, or COOC.
COOC. You just mentioned the safety element out of context. That sounds particularly intriguing, especially for our more technically inclined listeners. What exactly is that, and how does it relate to tailoring safety activities?
ECOC is a fascinating and increasingly common concept in automotive development. It refers to an element, let's say a specific integrated circuit designed for sensor processing, or a generic software library for motor control that is developed entirely independently of a specific vehicle item or application.
Developed in isolation, kind of.
Right. Its development is based on a set of general assumptions about its intended use and context. For example, a supplier might develop a power management chip, assuming it will be used in an environment with certain voltage ranges and temperature limits, and with certain safety mechanisms handled by the surrounding system.
Based on assumptions. Okay.
The critical catch with an SCOC, and this is where the rigor comes in, is that these initial assumptions must be rigorously validated when the element is finally integrated into its target application, its specific vehicle system.
So if the element was developed assuming one type of car, but now it's going into a completely different vehicle platform or a system with different operating parameters, you have to prove it's still safe and that all those original assumptions hold true in that new context.
Precisely. The standard reinforces a fundamental principle. Functional safety is ultimately an item property, not just an element property.
Safety belongs to the whole system, not just the part.
Exactly. What this means is that while an individual component might be safety-related and robustly designed, its ultimate functional safety can only be truly confirmed when it's integrated and validated at the vehicle level, within its specific operating environment, interacting with all other systems. This emphasizes the profound importance of vehicle-level validation to account for all real-world interactions, emergent behaviors, and the specific assumptions the SEOC was built upon.
So integration testing is paramount.
Absolutely. And this allowance for tailoring, whether it stems from an impact analysis or the integration of an SEOC, must be clearly defined in the central safety plan and backed by a robust, explicit rationale explaining why the tailoring is appropriate and sufficient to achieve the necessary functional safety. This is how the standard balances its inherent rigor with the practical realities of a fast-paced, supply chain-driven industry like automotive development.
That makes a lot of sense, especially in an industry that relies so heavily on complex supply chains and component reuse. So once you've done all this analysis and potential tailoring, how do you actually plan and coordinate all these safety activities across a project?
That's where the safety plan comes in, and it is truly a central living document for any safety-critical project. The safety manager is specifically responsible for creating and meticulously maintaining this plan.
The safety manager owns the safety plan.
Correct. It defines all the specific safety activities that need to be performed, the procedures to follow, any specifically tailored activities for this project, and crucially, it references those development interface agreements, or DIAs, for any distributed developments between different companies or departments. Each individual safety activities plan within this larger document must be incredibly detailed.
How detailed?
Including its objective, its dependencies on other tasks, the person responsible for it, the required resources, the timeline, and the associated work product that will be generated. And this isn't a static document, it's dynamic, meant to evolve with the project.
A living document.
Yes, it must be updated incrementally, at a minimum at the beginning of each major phase, to detail the planning for that specific phase. All work products required by the safety plan must also be meticulously kept up to date throughout development until the product is finally released for production.
It sounds like an incredibly detailed roadmap that truly evolves with the project, ensuring safety is never a forgotten step. And how does the standard ensure that the safety lifecycle actually progresses correctly? Are there gatekeeping mechanisms to prevent rushing through critical steps?
Yes, absolutely. There are critical gatekeeping mechanisms, and Clause 6.4.7 directly addresses the progression of the safety lifecycle. It states unequivocally that a subsequent subphase only starts if a lack of information or unresolved issues from preceding phases does not cause an unreasonable risk regarding functional safety.
Only starts if the previous phase is solid, basically.
That's the essence of it. This is a crucial checkpoint. It means you can't just move forward and hope for the best if foundational safety information or verification from an earlier stage is missing or incomplete. It forces a methodical, evidence-based progression.
So it prevents rushing through development with adequate safety assurance, potentially pushing risks down the line. It sounds like a lesson learned from many industries.
Exactly. Furthermore, all work products, every document, every piece of code, every test report must be under formal control. Configuration management, robust change management, and proper documentation.
Formal control, configuration management, change control.
Yes. This formal control needs to be in place no later than when the project enters the product development at the system level phase. This ensures meticulous traceability, strict version control, and clear accountability for all safety-related documentation throughout the entire development process. You know exactly what version of what document was used and who approved it.
This all builds up to one grand argument for safety, doesn't it? The safety case. What exactly is that, and who is its audience?
The safety case, covered in Clause 6.4.8, is indeed the core concept here, the culmination of all the efforts. It's developed to provide the comprehensive argument for the achievement of functional safety. Think of it as the compiled evidence, the legal brief, if you will, that conclusively proves the item is safe.
The proof that it's safe.
Right. It's not a single monolithic document, but rather a progressive compilation of all the work products generated throughout the safety lifecycle that collectively support the overall safety argument. In complex distributed developments, the overall safety case can be a combination of the customers and various suppliers' safety cases, all meticulously cross-referencing evidence from all parties involved. It's the ultimate proof point, the definitive statement that functional safety has been achieved.
So it's the detailed story of how safety was built into the product, backed by every piece of documentation, every test result, every analysis. But who reviews this story? Who are the guardian angels, as our outline puts it, that ensure everything is truly on the up and up and not just a self-serving narrative?
That brings us to the crucial oversight activities known as confirmation measures, detailed in clauses 6.4.9 to 6.4.12.
Confirmation measures, okay.
Their primary purpose is to independently confirm the functional safety of the item or the contribution of developed elements. They are explicitly designed to ensure objectivity and, critically, to avoid conflicts of interest.
Independence is key here.
Absolutely. The standard defines different levels of independence for these measures, ranging from I0, which is essentially performed by a different person, all the way to I3, which is the highest level. Independent regarding management, resources, and release authority from the department responsible for the creation of the considered work product.
I0 to I3. Higher number means more independent.
Correct. This commitment to unbiased review, to having a truly fresh set of eyes, is a cornerstone of the standard because it actively prevents groupthink or internal pressures from compromising safety judgments.
I can absolutely see why that's so important. You definitely don't want the same team that built something to be the only ones judging its safety. Let's delve into the specific types of confirmation measures. First, confirmation reviews. What do they focus on?
Confirmation reviews, covered in 6.4.00, focus on judging whether key work products, specific documents, designs, or plans provide sufficient and convincing evidence of their contribution to functional safety. These reviews are critical, and the standard mandates specific levels of independence for each, depending on the ASIL and the criticality of the work product.
So independence depends on the ASIL.
Yes, generally higher ASIL means higher required independence. For instance, the impact analysis at the item level requires I3 independence for all ASILs from A to D.
I3 for all ASILs on impact analysis. Wow.
Yeah. The review here judges if modifications are correctly identified and if their safety implications and necessary activities are adequately assessed. It's an early critical gate.
So even for the initial assessment of a change, you need that high level of independent scrutiny. That sets a very high bar right from the start.
It truly does. Another crucial one is the hazard analysis and risk assessment, or HAR.
The HAR, very foundational.
Extremely. This also requires I3 independence for all ASILs. This review checks if the operational situations and hazardous events are appropriately identified and described, if ASILs and QM ratings for less safety-critical functions are correctly determined, and if safety goals adequately cover all identified hazards. It also ensures consistency across comparable items and meticulously evaluates the soundness of rationales for the ECS parameters exposure, controllability, and severity, which are the foundational inputs used to determine the ASIL.
So independent check on the risk assessment itself, vital. What about the safety plan itself? Does that central document get reviewed by independent eyes?
Yes, the safety plan itself undergoes a rigorous confirmation review. Its independence level ranges from I1 for lower ASILs like QM or ASIL AB, up to I3 for ASIL D, reflecting its increasing criticality.
I1 to I3 depending on ASIL for the safety plan?
Correct. This review ensures the safety planning is consistent with the initial impact analysis, the overall project plan, and critically, the resource allocation. It scrutinizes any applied tailoring, especially for proven in-use arguments, checking the justification, the efficiency of field monitoring data, and any candidate changes. It also critically examines the distribution of responsibilities in distributed developments, ensuring no gaps in accountability.
So the plan itself is rigorously checked. And what about the safety concepts, how you intend to achieve safety? The FSC and TSC.
Both the functional safety concept, FSC, and the technical safety concept, TSC, also undergo confirmation reviews, with independence from I1 for ASIL AB up to I3 for ASIL D.
Same independence range, I1 to I3.
Yes. These reviews assess the feasibility and appropriateness of the concepts considering all prior safety analyses, like dependent failure analyses, which identify cascading failures. They also check the adequacy of the proposed safety mechanisms, the effectiveness of warning and degradation strategies, what happens when a system fails safely.
Graceful degradation.
Right. The validity of any ASIL decompositions, and ensure that all assumptions made during the design process are explicitly and clearly documented. And a very important point for all confirmation reviews is that they must be finalized before the release for production. This is a non-negotiable gate, a true stop work point if not completed satisfactorily.
Okay, so reviews of key documents and plans by independent parties must be done before release. What's the next layer of guardian angel oversight?
That's the functional safety audit described in 6.4.11. While confirmation reviews focus on the output, the work products, the audit evaluates the implementation of the processes required for functional safety.
Audit checks the process, review checks the output. Got it.
Exactly. It's essentially checking if you're actually doing what your safety plan says you're doing. It's required for items with A cell, B, C, or D, and also must be finalized before release for production.
B, C, D for audits. Okay.
An audit checks whether processes are being implemented as defined in the safety plan, if safety plan products comply with organizational rules, if the arguments for achieving ISO26262-Part objectives are sound, if work products are available and consistent, and it provides recommendations for continuous improvement. It can be performed or synchronized with automotive SPICY assessments.
SPICY, right.
Which is another industry standard for process capability, but it's important to note it's not a substitute for a full functional safety assessment.
So an audit checks if your actual practices align with your documented processes, and then the big one, the ultimate judgment call, the functional safety assessment. This sounds like the final exam for the entire project.
Indeed. The Functional Safety Assessment, or FSA, detailed in 6.4.1, is the highest level of judgment. It assesses whether the achieved functional safety of the item or the contribution of developed elements is truly sufficient and robust.
The final judgment on safety achievement.
That's it. Like the audit, it's required for items with AC Style B, C, or D. It's planned very early in the project, ideally at the start of system-level development, performed progressively as the project matures, and must be finalized before release for production. There's no getting around this.
Also required for B, C, D, also before release. What's the scope of this assessment? How broad is it? Does it pull everything together?
It has the broadest possible scope, encompassing the entire safety plan and all required work products, all processes, the effectiveness of all implemented safety measures, the full safety case arguments, and the rationales for closing any and all safety anomalies. It meticulously considers the results from all previous confirmation reviews and audits, essentially summarizing and validating all prior safety efforts.
The grand summary and validation.
Pretty much. The outcome of the FSA is incredibly critical and carries immense weight. The assessment report provides a definitive recommendation for acceptance, conditional acceptance, or rejection of the achieved functional safety.
Acceptance, conditional acceptance, or rejection. Stark choices. What are the consequences if you get a conditional acceptance or, worse, a rejection?
If it's a conditional acceptance, it means specific conditions and open issues must be addressed and resolved before full, unconditional acceptance can be granted, usually with a deadline.
Okay, fix these things first.
Right. If it's a rejection, then adequate corrective actions must be performed, and the functional safety assessment must be repeated, potentially forcing significant delays in re-engineering. This is truly the ultimate gatekeeper, ensuring that products only move forward into mass production once a profoundly high level of confidence in their functional safety has been objectively established by independent means. There's no room for shortcuts here.
So all these measures build up to one monumental decision, the release for production. This sounds like the absolute point of no return.
Absolutely. The release for production is covered in 6.4.13. Before this decision can be made, two non-negotiable prerequisites must be met. The safety case, that comprehensive argument for safety, and all applicable confirmation measure reports from the reviews, audits, and assessments must be available and satisfactory.
Safety case and confirmation reports, ready and okay.
Yes. Approval for release is only given if there is sufficient evidence for confidence in the definitive achievement of functional safety. This cannot be rushed, cannot be overridden by commercial pressures, and cannot be based on incomplete data.
So no skipping steps, no compromises on the evidence.
Precisely. It's a formal and incredibly rigorous approval. The release documentation must include the name and signature of the person responsible for this final decision, the specific versions and configuration of the item, and the precise release date of the item or its elements.
Formal sign-off.
Yes. And crucially, at this point, a definitive baseline for the embedded software, including any calibration data, and a definitive baseline for the hardware must be available and meticulously documented. This provides a clear, controlled reference for the product as it enters series production, serving as the formal declaration that, from a safety management perspective, the product is indeed ready for the world.
The official starting point for production, and what are the tangible work products that ultimately result from all this incredibly detailed, project-dependent management? What's the paper trail?
The standard specifies them very clearly. The impact analysis reports, both item and element level, the comprehensive safety plan, the definitive safety case, all the confirmation measure reports and those independent reviews, audits, and assessments, and finally, the formal release for production report. These are the critical documents that collectively prove that functional safety has been managed rigorously and systematically throughout the entire development journey of the product.
So, the car is designed, developed, meticulously assessed, and finally released for production. A monumental achievement. But does ISO 26262's involvement stop there? Or does the safety management extend throughout the vehicle's entire life on the road, long after it leaves the factory floor?
That's an excellent question, and the answer is a resounding no. The involvement absolutely doesn't stop. Clause 7 of the standard, titled Safety Management Regarding Production, Operation, Service, and Decommissioning, addresses precisely this.
Clause 7, the long haul.
Exactly. The objective here is to define the ongoing responsibilities for achieving and critically maintaining functional safety throughout the vehicle's long life beyond initial development and sale. Safety, in the context of this standard, is a continuous lifecycle commitment, not just a development phase that ends with release.
So it's about continuous vigilance and safety even years after it leaves the factory floor and drives off the dealership lot. When does the planning for this post-development phase actually begin? Do they wait until the car is out there?
No, absolutely not. That would be far too late. The planning for this critical post-development phase begins remarkably early in the process, specifically during the product development at the system level, as defined in Part 4 of the standard.
Planning starts way back in system development. Wow.
Yeah, this foresight ensures that considerations for manufacturing processes, ongoing maintenance, potential service needs, and even end-of-life decommissioning are integrated into the design process from the very beginning. Key activities for this phase include appointing responsible persons for these ongoing tasks and meticulously planning and executing activities according to ISO 26262-Part.
Part 7 covers this phase specifically.
Yes, Part 7 details these specific post-development requirements.
And what specific processes are required for this ongoing management? What does maintaining safety in the field actually look like for a car manufacturer?
Organizations must institute and maintain robust processes to achieve and maintain functional safety during these operational phases. A key part of this is establishing a comprehensive field monitoring process for the item's functional safety.
Field monitoring. Watching the cars in the wild.
Exactly. This means actively collecting and analyzing data from vehicles already on the road. It's not just about waiting for a recall or a customer complaint. It means companies are constantly looking for patterns. Is a particular sensor failing more often than expected in a certain climate? Is a software module crashing more frequently in a specific driving scenario? This proactive approach allows them to identify potential safety issues before they escalate.
Catching problems early.
Right. Sometimes even pushing out over-the-air updates or issuing service bulletins to prevent problems from becoming widespread.
So it's about proactively monitoring for issues and ensuring that any changes, even those made years after the car is sold, are still subjected to the same safety discipline. That's a huge undertaking.
It is indeed. And speaking of changes, if the item changes during production, operation, service, or decommissioning, for example, a software update, a recall fix, or a service procedure performed at a dealership.
Like an OTA update or a repair.
Exactly. The original release for production documentation must be updated accordingly. These changes are not ad hoc. They are subject to strict change management processes, ensuring that even post-production modifications are handled with the same safety rigor and documentation requirements as initial development. It's a continuous safety loop.
So change management never stops. And what are the work products for this phase? How do they prove they're doing all this?
The primary work product here is simply evidence of safety management regarding production, operation, service, and decommissioning. It's the compiled proof, the record keeping, that the organization has fulfilled its ongoing responsibilities for maintaining safety in the field, diligently monitoring and responding to issues throughout the vehicle's entire operational life.
Now let's talk about something incredibly timely and increasingly important in the automotive world. The evolving complex relationship between functional safety and cybersecurity. Clause 5.4.2.3 and Annex E of the standard explicitly touch on this. Can you help us understand this crucial interaction, especially as vehicles become more connected and autonomous?
This is a critical discussion, especially as vehicles transform into rolling computers deeply integrated into the digital world. Annex E provides detailed guidance on the potential interaction between these two vital domains.
Guidance, not requirements.
Primarily guidance in this annex, yes. It's not about prescribing how to achieve cybersecurity, but about the interface and coordination with functional safety. The core difference between them is vital to grasp. Functional safety fundamentally deals with issues arising from unintended malfunctions. That's your systematic and random faults.
Accidental failures.
Right. Think of a software bug, a component wearing out, or an electrical short circuit. Cybersecurity, on the other hand, deals with issues resulting from malicious intent external to the EE system. This is about attacks, hacking attempts, or unauthorized access aimed at manipulating or disrupting the system.
So one is about accidental failures, the other is about deliberate attacks. Why do they need to interact so closely if they're distinct? Why can't they just be separate disciplines?
Because knowing relevant cybersecurity information can either negatively impact functional safety or, conversely, it can powerfully support its achievement.
How so?
Well, imagine a scenario where a successful cyber attack leads to a system malfunction that violates a safety goal, perhaps by spoofing sensor data, causing unintended acceleration, or disabling a safety-critical feature like anti-lock brakes.
A cyber attack causing an unsafe state.
Exactly. Conversely, a cybersecurity countermeasure, if poorly designed or implemented, could inadvertently interfere with a safety mechanism, potentially causing a new functional safety hazard. So while the annex isn't about prescribing how to achieve cybersecurity itself that's covered by standards like ISO26262-Part
21434 for cybersecurity.
Right. It's very much about understanding the interface with functional safety and how they must be coordinated to ensure overall vehicle safety in an increasingly networked world. The consequences of both accidental malfunctions and deliberate attacks can lead to the same hazardous outcome: loss of vehicle control or injury or death.
That makes perfect sense. They might be different domains with different root causes, but their consequences can certainly overlap. So how does the standard suggest they interact across the entire life cycle of a vehicle?
The standard identifies key interaction points at different phases, emphasizing coordination and information exchange. At the functional safety management level, it recommends explicitly coordinating plans and milestones for cybersecurity activities with those for functional safety.
Coordinating the planning.
Yes, this helps understand dependencies that could influence safety planning, such as the selection of secure tools or programming languages, or the need for specific hardware security modules. It also suggests harmonizing the management of field monitoring activities for both cybersecurity and functional safety.
Joint field monitoring.
Harmonized, yes. This includes integrated incident reporting, robust tracking, and coordinated resolution processes. This ensures that if a cybersecurity incident impacts safety in any way, it's communicated effectively, investigated jointly, and resolved in a coordinated manner to prevent recurrence.
So, if a vehicle system gets hacked and it affects, say, the steering, both the cybersecurity team and the functional safety team need to be on the same page for investigation and fix, understanding both the malicious intent and the resulting functional malfunction.
Exactly. Then, in the concept phase, there's a crucial integration point. Cybersecurity threats should be analyzed as hazards from a functional safety perspective.
Treat cyber threats like any other hazard in the HATEC.
Essentially, yes. This means that during your initial hazard analysis and risk assessment, your HATEC, you're not just thinking about accidental failures, but also about what happens if a malicious actor tries to take control or corrupt data. This ensures that the HATEC and the resulting safety goals are comprehensive and account for potential malicious intent.
Widening the scope of the HATEC.
Precisely. Functional safety, in turn, provides vital information, like identified hazards and risks, to aid cybersecurity in their threat identification and risk assessment. Conversely, cybersecurity strategies or countermeasures, like how an EE system behaves if an attack is detected, need to be carefully considered for their potential impact on safety goals or concepts. This is critical because a cybersecurity measure, if not designed with safety in mind, could inadvertently trigger an unsafe state.
So, thinking about cyber threats from the very start, right alongside other potential hazards, creating a layered defense.
Precisely. During product development, the interaction becomes even more granular. Technical information on cybersecurity strategies and countermeasures directly impacts the technical safety concept and the overall system design. Cybersecurity software and hardware design considerations influence the achievement of safety requirements and design constraints, such as the necessary independence between components.
Safety informs cyber, cyber informs safety design.
It's a two-way street. Functional safety, in turn, clearly communicates its design constraints to the cybersecurity teams. Analysis activities for both safety and cybersecurity can and should be harmonized to uncover potential cybersecurity impacts on functional safety, and safety analyses can specifically consider the effect of cybersecurity measures. It's also recognized that some cybersecurity countermeasures, like robust software integrity checks, might address certain systematic failures, potentially sharing methods with functional safety measures, creating a more robust overall system.
Finding synergies between the two.
Exactly.
It's truly a continuous dance between these two critical disciplines, constantly informing and influencing each other. And what about during the production and operation phase, once the vehicle is out there?
In production and operation, the interaction focuses on cybersecurity incident resolution strategies. Any design changes that result from a cyber incident response, like a software patch to close a vulnerability or an update to an intrusion detection system, need to meticulously consider their potential impacts on functional safety.
Don't let the cyber fix break safety.
That's the core idea. This ensures that fixing a cyber issue doesn't inadvertently introduce a new safety hazard or compromise an existing safety mechanism. It's about maintaining that delicate balance throughout the entire lifespan of the vehicle.
So whether it's an accidental malfunction or a malicious attack, the overall goal is undeniably the same: to ensure the safety of the vehicle and its occupants above all else. This interconnectedness highlights how broad and demanding modern vehicle safety management has become.
Precisely. The standard doesn't just address the immediate technical safety, but extends its reach to embrace the evolving threat landscape, reflecting the complex, connected reality of modern vehicle systems. It's an ongoing, living standard designed to adapt. #DR.
Today, we've taken a deep dive into ISO26262-Road Vehicles Functional Safety Part 2, Management of Functional Safety. What we've truly revealed is that functional safety in road vehicles is far, far more than just the technology itself.
So much more.
It's about a holistic, deeply integrated management approach, encompassing a robust safety culture, rigorous processes for managing anomalies, ensuring competence across the entire organization, and implementing layered independent confirmation measures at every single stage of a product's life.
From cradle to grave, really.
Exactly. From the initial concept and meticulous development to painstaking production and even graceful decommissioning, this standard provides the foundational blueprint for building trust into our vehicles, giving us confidence every time we drive.
And the continuous evolution of this standard, particularly its proactive integration with cybersecurity, truly underscores the dynamic nature of vehicle safety. It's not a static target that you hit once and forget about.
Set it and forget it. No way.
No way. It's a moving one that constantly adapts to new technologies, new threats, and new industry challenges.
So, to distill our deep dive into a few key takeaways for you, our listener. First, process is paramount. Safety isn't accidental. It's the direct result of meticulously defined and diligently followed processes, from the initial design and analysis all the way through to real-world field monitoring. Every step is intentional.
Second, and this is so critical, culture matters. A strong, ingrained safety culture is the invisible yet absolutely vital foundation that supports all the technical efforts. Without that organizational backbone, even the best processes and technology can, and often do, falter. It's about the mindset as much as the methodology.
Third, independence is key. The multi-layered confirmation measures and varying levels of independence ensure objective oversight and critical scrutiny. This prevents conflicts of interest, challenges assumptions, and ensures a truly unbiased assessment of safety, acting as crucial guardian angels.
Fourth, adaptability is essential. The standard's thoughtful provisions for tailoring and impact analysis, whether for modifications or the reuse of components like SEO-CALs, allow for necessary flexibility within a rigorous framework. This is crucial for a fast-evolving industry like automotive, where innovation must coexist with uncompromising safety.
And finally, interconnectedness. Functional safety isn't isolated in its own silo. As we discussed with cybersecurity, it's increasingly intertwined with other critical areas, demanding a holistic, integrated approach that considers all potential influences on vehicle safety.
As our vehicles become ever more autonomous and connected, relying on incredibly complex electrical and electronic systems and interacting with an increasingly networked world, it raises an important question for you to ponder. What further challenges do you foresee for functional safety management in the coming years?
How might the human element of controllability, that innate ability of a driver or pedestrian to avoid harm, or the ever-present, evolving threat of sophisticated cyber attacks push the standard to evolve even further? What new questions does this deep dive raise for you about the future of vehicle safety, and what innovations might emerge to meet those challenges? We hope this deep dive has given you a fresh perspective on the invisible layers of safety that protect us on the road every single day.